All right, let's get started. All right, so my name is Michael Park. I'm going to be talking to you about code indexing at Meta today. The system that I'm going to be presenting is called Glean. I'm a software engineer at Facebook, Meta. I work on developer experience, developer tools, on a team called Native Languages Developer Experience. So I have a sweater that has C++ and Rust on it because those are the two areas that we help with. I obviously work on the C++ side of things. But this is a general code indexing system, and so I'll go over the architecture of that. I'll motivate the talk a little bit as to what we're trying to do. I'll go through an architecture overview of Glean. We'll have some fun with C++ macros, because this is going to be a focal point of providing go to definition experience for macros. And we need to understand macro locations to do that. I'm going to introduce Angle, which is the schema definition and query language. And then we'll go back to C++ macro navigation. OK, so motivation. The general motivation is to help developers feel delighted when they do programming, right? When I read code and I want to do some go to definition, if it doesn't work, it's really frustrating. So this is Clang D doing the job of go to definition, and being able to jump into a new code base and being able to browse the code base easily is a very important feature. Here's an image from CLion. So on the left, you can see an outline of the file. You can see a hover card over vector, right? And it gives you a bunch of information, like what namespace it's in, the signature. It even has a link to CPP reference for vector pushback, which is quite nice. So all of these tools are going to go and look at your code some way or some form to be able to collect data to be able to provide this experience, right? For example, in CLion's case, like it has to have looked at the function and pull various information about that function to display it for you in this way. Another tool that looks at your code and tries to provide good experience is documentation tools, right? So this is a snapshot of Doxygen, where not only does it pull information about the code, but it's going to pull the documentation that's attached to the code and try to display for you in some meaningful way. It's even going to link different functions to each other, so you can already see like similar logic is being done by the Doxygen tool as well as Clang D, right? Because they need to figure out like what functions refer to what other functions and stuff like that. And there are a lot of other developer tools, right? So IDEs, VS Code, CLion, IntelliJ. I've shown some examples of that. There are some web-based code browsers that don't necessarily have a local box to work with, or even a checkout of the code. Documentation generation I just showed, but there are other tools like symbol search, where you might want to figure out like, oh, where are all the places in my code base where a variable is named underscore, right? If you're trying to steal that for pattern matching or something, you might want to figure out how often is this thing used. And so if you go grep for underscore, I mean, that's not going to be a good time, right? Even if you have some form of symbol search, it's going to give you like all the functions that may be named underscore, macros, all the other things, but then are you able to actually ask it, like, give me variables that are named underscore? That's a slightly different query. Code analysis tools like linters and dead code detection also need to look at code and analyze it. The last bit there is API usage tracking. So this is useful for like library maintainers, right? So if you have some function that you want to deprecate, and maybe you have like 10 references left, and if you can find that out quickly, then you might say, okay, let me just do this by hand and get rid of it, right? But all of these tools and functionality exist, but there are various limitations. So many tools are language specific, naturally. So for Clang D, for example, it supports C, C++, Objective-C. Documentation tools generally tend to be pretty language agnostic. But a lot of times, because it became language agnostic, it misses a lot of the language details, right? Scaling to large code bases can be often challenging. When you use Clang D, which is a great tool, by the way, if your code is relatively large, you're going to sit there waiting for indexing to finish for some time. And I alluded to this a little bit, but the collected data by these tools are not available for generic queries, right? So the variable name size I already told you about. But like, let's say, for example, your documentation tool, you know that it went and looked at all of your functions and tried to grab the associated documentation for it, right? And so it saw all of your functions and the documentation corresponding to it. So if a function is not documented, then like it has all the information to be like, okay, you have 80% of your functions are documented, there are 20% that are not, and here they are, right? But like those APIs don't exist for Doxygen. And so maybe you go into Doxygen, hack it up, and then try to get that information, right? But that's a very one-off kind of solution for a very specific thing. And so what we want is to be able to ask your tool about general questions about the code. So we want to scale this up, but we want to scale it up in several different axes. We want to be able to support many languages, scale to large code bases. We want to be able to power many of the developer tools that I just shared. We want to be able to serve complex queries, so some examples that I already gave. And then the schema that we develop has to be extensible to be able to collect more data, because we're not going to be able to store the entire AST. That's just going to be too much information. And so this brings me to Glean, and the description for Glean is system for collecting, deriving, and querying facts about source code. So I like to think of Glean as more of a code indexing platform, and I'll get into what I mean by that. Yeah, Dave?
Just a clarification question. When you talk about extending the schema, I didn't understand what that meant.
So yeah, I'll talk more about that, but basically we need some schema to communicate between the tools that index information and then the clients that want to query the information. You need some API to request those information, right? And so the schema is going to describe the way, the organization of the information that we're collecting about the code, as well as how the clients are going to get access to that information. And so if that schema is too strict, then but I'll get into it. Yeah. Okay, any other questions at this point? Okay, let's go. Let's move on. So I'll go over an architecture overview. So we have Glean in the middle, and we're going to have a bunch of languages that we're going to support. So we have C++, let's say Hack, Haskell, and JavaScript. And I list these because these are the I guess, custom indexers that we maintain internally. But it's also open sourced. Okay, so we're going to use the front ends of all these languages to get the AST. And then we're going to send a bunch of data to Glean, which then is going to be collected. And so as a collective, these are the indexers of the system. So my area of maintenance and development is mainly in the C++ indexer. So even though I'm telling you about Glean as a system, I don't really work on Glean core all that much. But of course, I need to understand it to be able to use it. Okay, Glean uses RocksDB as the storage backend. So this is the storage layer. I'm not going to say anything more about that than this. We're just going to treat that as a black box as to how they do that stuff. On the right, we're going to have all the different clients that we're going to support. So we have IDEs, code browsers, stack analysis, API usage. We've already talked about these. So all of these clients are going to send requests to Glean, and Glean is going to read the data that it wrote to RocksDB and then respond. Right? So this is why we need a schema, because at this point, we have the interactions that we have with the indexers, as well as the interactions that we have with the clients, and we need to have some mechanism of communicating between those components. So defining the schema. So Glean doesn't enforce a single schema, and this is very important. Each language has their own nuances, even something universal as variable declarations, which virtually every programming language would have. There are all these different traits, characteristics about them, right? Like, so in C++, like variables can be templates. It can be marked context for initialization that's used to initialize that variable. Like, all these things are different. And even within the same language, different clients actually need different data. So static analysis needs precise information, but code navigation will be fine with heuristics. And I'll give you examples of exactly what I mean by that. So one approach to do this, and other systems that have support this kind of operation service will do something like this. So skip, for example, is a format by source graph by which they try to narrow down a least common denominator of all the different languages so that you can support language agnostic queries. And so code browsers, for example, would access schema like this to be able to do its job. The problem is, if we want to build a language-specific tool like that includes removal for C++, trying to use a schema like this is just not going to work at all, right? And the reason why I can say that so confidently is because tools like include what you use, and now Clang has a tool called include cleaner. Those tools have the full access to Clang AST, and they still have trouble, right? And so if we have a hard time doing that job with the full AST, a trimmed down schema is not going to do the job. The other alternative is to union all of the languages and the characteristics about them. But this schema is going to be massive, and you're going to have all these different parts of the schema where it's like, okay, static applies to C and C++, but const expr is only for C, C++. Haskell has this other thing, right? And like you're going to have some parts that are common, but there's going to be so many language-specific stuff that live in that schema. It would be really difficult to work with. So what we do in Glean, we're going to split this up. And we're going to split this up into the multiple schemas. And so we're going to have a schema for C++, we're going to have a schema for Hack, we're going to have a schema for Haskell. That shield-looking thing in the middle is the intersection. And this is a layer that we call code markup. So what we're going to do is derive this commonalities between the languages by a step called derivation. So because the language-specific schemas will have superset of the information, we should be able to describe the deduction rules from the language-specific stuff to the code markup layer to be able to support tools like code browsers. But this gives us a chance to at least do language-specific tooling, right? So that include removal for C++, for example, wouldn't go to this code markup schema. It would go to the C++ schema. So here's an example where even for the same language, different clients might want different data. So let's describe the code a little bit. So we have the two are identical, by the way. There's no tricks here. So we have some n : foo function. We have a macro definition which it expands to n : foo. And so inside this function bar, we can invoke that macro, and we're gonna have the same thing on the right hand side. So on the left, let's say we want for static analysis, what we want precise information. So by precise information, what I mean is like when we're trying to deduce, let's say for example, like whether bar refers to foo, right? We can see because of the macro expansion inside bar that the reference to foo is really occurring from inside the bar body, right? And that's just like by the rules of the language as to how that happens. On the right, but like, okay, so for example, in here, let's say we build code navigation with this information, right? Then you would click on macro, the yellow highlighted area, and it might ask you, did you want to go to the macro or n or foo, right? At which point you'd be like, take me to the macro, it's called macro. Why are you even asking me about n and foo? And there's no n or foo here. But you do have n and foo there in that location. That's not what you want for code navigation. So on the right for code, this is kind of what you want for code navigation, right? The macro should go to the macro, and the n and the foo you want to go to the corresponding bits of code. Yeah, right.
It sounds like you probably augment the AST with the preprocessing tokens and things like that. Is that a strict AST? Is that right?
Augment the schema.
Well, because like an AST usually. Well, AST is usually constructed post preprocessing. So
correct.
The invisible, so there's some kind of extra.
Exactly. So during the preprocessing stage, we're going to collect a bunch of data, and then. But the other part is, even though the preprocessing happens before the AST, the information is actually preserved in the AST. Okay. So in the expanded code that the AST is representing, you can ask it to get the spelling locations to get to like inside the macros. And I'll discuss it in the C++ macros section. Okay, so any other questions? Okay. Okay, so the question is like, can't we actually use the code navigation kind of model to do static analysis? Because transitively, if we say bar refers to macro and macro refers to foo, then can't we just deduce the fact that bar refers to foo? right? The problem is macros are horrendously evil, right? So if you can have a different foo, a : n : foo, and that macro could be expanded right after an a : right? So now, on the left, the precise information tells us that a refers to a, and this version of the macro refers to a and foo, right? Whereas on the right, we might have two references from inside the foo macro definition, and it's going to, and if we try to do that transitive call graph, we might say bar refers to macro, and macro refers to two different foos, and now we think that bar refers to both foos, which it does not, right? And so there's this tension of like, well, do we want this to be precise for analysis, or do we want it to be useful for tools like code navigation? So let's get into some more macro, understanding these locations. So here's client D trying to do this job. Here's some more horrendous macros. Let me describe it a little bit. So we have this stat macro, which takes some parameters. And we have this stat t variable named s. Now, importantly, when you look at the bottom of that macro, you see s.data space underscore data assignment, right? Okay. When we call that stat macro, we're gonna on the right you see .uint64 equals value. That's not named arguments, right? That's just text being pasted into data assignment, and ultimately this is going to expand to s.data.uint64 equals value. Okay. And so, and we have several of these patterns. We have the dot .int64 and dot .string at the bottom as well. And so, trying to do code navigation in this area, how many people are confident that it'll work well? Okay, maybe a loaded question, but nobody raised their hand. So most tools will just give up. Let's see how client D does. It actually does better than you would think. So it jumps to uint64 in that stat t class. In 64, there are 3 results. This one's in G flags. This one's in some other Google namespace. What's happening there? String. Oh, we're in this std string definition. Okay, what's going on? Aggregate. Hey, that worked. Great. What about data? Hello? Oh, doesn't work? Can I do local variable jumps? Like this s? It's right there. It's right there. Just do the thing. Stats worked fine, right? We were inside the macro definition. We click on stats and we jump to the parameter. So it's like kind of weird. Like I don't really know what's going on here. My best guess is that it's doing a text-based search for heuristics, right? So like, if there are no other variables named uint64 in your index, maybe you just jump there, right? But like in 64, clearly it saw multiple versions of that, and so it gave you the options that it saw. But it's not actually doing the expansions and linking to understand what's actually happening. So a lot of heuristics-based stuff going on here. Works well sometimes, kind of confusing as to why, like the dot data didn't work, for example. I don't know. Okay. So there are 3 types of locations that we need to be mindful of. And generally, like when we talk about macros, we just kind of say, oh, it's terrible, and we leave it at that. But let's get into some details of it. So the first type of location is a file. And what that means is just non-macros. So if you don't have macros involved at all, then it's going to be then that token is going to live in a file location. The second type is expansions. So these are the sites where your code lives. So the expansion site, I mean. So it's generally going to be where the macro is used. The third type of location is a spelling. So there are 2 types of spellings. One is inside a macro body, and the other is a macro argument. So because macro arguments, even though they're not really inside a macro definition, it's going to be inside the macro definition, right? So Macro arguments are actually a pretty deceptive form of spelling locations because they generally don't look like spelling locations. They generally don't look macro related. So we need to basically keep track of this set of relationships between starting from a file, expansion, or spelling, and then you might end up at any of file, expansion, or spelling. And as I said, spelling, there's 2 types, and so this is actually a 4x4, 16 different options here. Here's some common examples, and some of those variations are more common than others, right? So the first one is very familiar, going file to file. The second one is if you have some macro that defines entities and you can refer to it, then you can go from file to spelling, where the spelling is a macro argument. And so, G flags, for example, will do this kind of stuff, right? You do like define bool, some flag name, and then that's going to generate some variable that you refer to in that macro definition. We also have spelling to file. So here's one where the macro foo will expand to foo. And so this is a spelling macro body to file, right? So this will be like the stats example that we saw. Inside the macro definition, you're going to jump out to a file location. And as I said, the macro argument spelling locations are very deceptive because looking at assert foo greater than 0, you might not have thought that foo has to do with macros, right? You would think that the jump from foo to foo inside the assert might actually just be a regular local variable, local jump. Not local, sorry, it's a function jump. Here's another example that comes up relatively often, and we saw an example of that where we had the variable s and the use of it inside the same macro body, but like you couldn't jump there, right? But this is a spelling to spelling jump, which is within the macro body. Okay, so I'm going to introduce Angle now, and we're going to build a small language. It's going to, by the end of it, we're going to have something that looks like it should be able to index some very simple C++. I'm not going to show you the full C++ schema because this is going to be too much to deal with, and I want to build this up because none of you would have seen this before just now. So with Glean, we deal with predicates and facts. So predicates are basically types, and facts are values. And so we have, so here we have a schema called example, and we have 2 predicates. We're going to say name and qualified name. And so the name is just a string, and the qualified name has 2 fields, name and namespace. So of course, this should really have a list of namespaces or something like that, so, since you can nest arbitrarily. But in this example language, we're just going to say you have 1 namespace, and that's it. Each fact is assigned an ID in the database, and it's going to look at every fact and inspect any duplicate facts and unique them. And so if a fact has the same data, even if you try to insert it multiple times, it's going to deduplicate that and store that exactly once. And this is critical for us because we're going to have indexers that send facts from many different machines. And even if it were from a single machine, we're going to have build systems that build all these different translation units, and it's going to discover the same header like thousands and tens of thousands of times, right? So for example, like optional.h, if you build 5 different translation units, at some point you're going to find optional.h. But all of those are being discovered separately, independent of each other. And so when we go and write the fact that's related to optional.h, we want all of those to collapse into a single version. And if, for some reason, we have builds where we're building with different configurations, such that we actually see 2 different versions of the header, we actually want the 2 different versions to be stored in the DB so that we can analyze them. And maybe we merge them later or whatever, but we want to keep track of all that information. Facts are sorted by prefix for efficient queries, and I'll give you an example of what that means. It's not super important, but it's one of those properties that you want to understand about the system. And the queries are going to generate facts in a sequence, and I'll show you examples of that. Okay, the fact ordering example. So on the left, I have kind of an example database with 6 different entries in it. On the right are example queries. And so these are ordered in lexicographical order. And the reason for that is because if it's sorted this way, and you have all of the information for a prefix of a query, then you can just do binary search on a column-by-column basis to be able to do efficient queries. This is mostly a mental model for myself when I work with Glean. The details, I'm sure, are significantly more complicated. So the first query there, where we specify A2, is going to do a binary search on the first column and find a range of entries that match. And it's going to yield each of those entries one by one. And you can collect them and do your analysis there. So same thing here. Because the prefix, like we left a hole on the left-hand side, you can see that we no longer have a contiguous range that we can report, right? So now we need to actually scan the whole database to find our results. But it's still going to work. It's just going to take longer, and we're going to have to scan more stuff. Here's an example where both of them are specified. And this is just to give you a taste. Excuse me. So how do we actually produce these facts? Do you have a question?
So the fact ordering, is that like name is before namespace in this example here? So that's why name would be the...
Right, exactly, yeah. So name would be the left column and the namespace would be right column. And so if you wanted to search a qualified name by name, that would be fast. But if you wanted to see, find me all the names within a namespace, that's going to take longer, right? So this is a code snippet from the indexer, which is a recursive AST visitor with the Clang AST library. We have this visit namespace decal function, which is a callback that Clang is going to invoke during its traversal. And you see this line where we have db.fact of the example name. So the schema.h there is generated by the angle file, and then you're going to have it's going to be available to you for whatever language you want to do. So the angle file actually translates to Thrift, which can then generate a bunch of different languages. And so I'm using the C++ generation here to get this done. So there's this db utility that's provided, and so calling fact will generate that fact and send it to Glean, right? We're also going to get the return value of this fact call is going to be a fact handle. And so we're going to be able to refer to other facts with that handle that we get from facts. And I'll give an example of that in just a moment. So on the left is kind of an example code that we might want to index. 10 lines of code. It's still a lot of work. So on the right are some example JSON format data entries in that this indexer would have produced. So it would see names N1 and N2, as well as widget. The qualified names might be N1 widget and N2 widget. And here we have this is showing that each fact gets assigned unique IDs. And then inside here, these are references to other facts, right? So qualified name is going to refer to existing name facts. And so if there are commonalities, like widget in this case, it's going to be shared across the different predicates. So here's an example of some different queries. So the queries are structured like this. On the left is the name of the predicate. On the right is going to be a pattern. So in this case, underscore is a pattern, so it's going to match anything. And so this is going to basically just dump out all of the example.name predicate facts in the database. So we have 3 of those. We can do another shell query. On the left, we have qualified name, and on the right, we have another pattern. Now, the pattern is specifying that I want name to be widget. So in this case, we're going to spit out both N1 and N2 widgets. If you don't want the full fact, if you want to take a subcomponent out of the fact, then you can bind names to it. And this is getting very pattern matching, but I swear it's about Glean. So you can introduce a new name called NS, where, and then you write your predicate followed by a pattern, and namespace equals NS is going to bind the facts of namespace to NS, and it's going to yield that as the result. So in this case, even though we have basically the same query, it's going to only return the namespace portion of the qualified name. We also have bar, which is going to be an OR pattern. And so you can query for names that are N1 or N2, and it's going to give you these two results. Let's extend the schema a little bit. So we have names and qualified names. We're going to extend to introduce the record declaration. We call it record declaration, but it's basically just for struct, class, and union. We have a little enum that describes which one it is. We'll store a qualified name and the file line location. The location should be more elaborate than that, but for this example, we'll just keep it to a line number. So this is the Clang code that I would write for the recursive visitor. This is the part where we're building the name fact. So the first line of that you've already seen because we used that to build the example name, right? And then the second line there is doing the exact same thing for the namespace name. Then we're going to produce the qualified name by putting both those facts together. So you can see that I'm using the results of the fact call, the fact function call, to build these things up. We're going to grab a tag as to what kind of record it is, store that, and then we're going to bring it all together into a record declaration fact and send that to Glean. So the same code, using these rules, we would get these record declaration facts. And so you can see that they also get unique IDs. And these are, all, again, references to existing facts. So now we can build an xref. By the way, an xref is a cross-reference. So we're going to have the target, which is the record declaration, and the lines as to where the references to this record declarations are coming from. And then the predicate here is file xrefs, and so the file is going to be the file path, and then we're going to have a list of xrefs that occur in that file. So for example, for the code that we've been indexing, for the file xrefs of widget.cpp might be that target, which is the N1 widget, and then they're referred from lines 9 and 10. And so at this point, we have name, qualified name, record declaration, and file xrefs, which store some meaningful information about the code that we're indexing. So you can write a query. On the left, again, we have the predicate, name of the predicate, which is file xrefs. On the right, we have the pattern, which is the specific file we want to query for. And we would get the results like this. All right. Was that too fast? Everyone following? I think people are good. OK. Yeah, I feel like I was a bit worried about that part, but I think people are good. Yeah, David.
By the way, this is super fantastic. Is there any way that you can add additional schemas that might be domain specific for your particular code base?
Yes. Yeah. So like what I just did here, you could do yourself for some other language that you want to index, right?
I mean more like extending the C++ schema,
right,
to add some special nodes that make sense because you follow some kind of convention or something like that. Yeah. You could do that. Yeah. So this is like the extensibility of the schema is what I was alluding to earlier. You can just kind of extend it arbitrarily. Right? There's no restrictions there. Amazing.
Yeah. Okay, so we're gonna cover the code markup part of what I described in the architecture section. So this is gonna be derived predicates. Excuse me. Same example. We have file xrefs, which gives you some file and the xrefs inside of it, right? And let's say we want to write a new predicate called file to file. And all that's going to do is give me all the files that I refer to. And so rather than all the specific xrefs, I just want because I might have 1,000 xrefs from a file, but those 1,000 might refer to might be coming from 5 different files, right? So the predicate is going to look like this, file to file. The from and to are just strings, which is going to be file paths. And we can already do this, right? Because we have the querying power to do it. We can write a query like this, where we say from comma to where grab all of the file xrefs from an xrefs, and xrefs is an array. So xrefs square bracket dot dot square bracket is expanding that array. So we're going to iterate through every xref in this file, and we're going to grab the destination file of that xref, right? And then we're going to return the from and to pairs in sequence. But it's also going to do the deduplication, right? And so if we have something like main.cpp that refers to foo.h and bar.h, it's going to give you those two files, even if there are 100 references into foo.h and 100 different references to bar.h. This is going to collapse all that information. And this is going to be okay. So that's the query. Now, the predicate, before we had to have the indexer actually generate the facts and send it to Glean, right? But we can actually take this query and attach it next to the predicate. So at this point, you have a predicate that can be computed based on this query that we wrote. And this is going to happen on demand. And so when I now query, for example, that file to file, we're going to get basically the exact same result, except that the tuple field 0 and tuple field 1 have names called from and to. Okay? And so this is how we can build facts on top of each other. So now we're deriving this file-to-file facts from file xrefs. And the indexer didn't have to do any more work. Now, as far as efficiency goes, what I said is, file xrefs might have 1,000 different xrefs, but they might be pointing to 5 different files, right? So we're going to iterate over 1,000 xrefs and produce 5 results. And we're going to do that every time this query is invoked, right? Which can be quite expensive. And this is because we do the query resulting on query response on demand. But if we add a keyword stored in the middle, that one, then Glean is actually going to do the query but write the results into the database. So when I make that query on the right, file to file, now it's going to look at 5 facts as opposed to 1,000, because it's going to be stored in the DB. How much time we have? Okay. And we can do something similar. Oh, yeah.
Yeah, I just wanted to ask, so like if we have like a stored predicate like this, that just automatically gets recomputed every time we reindex, essentially? Or like, I was
Correct.
wondering, okay.
Correct, yeah. Yeah, so the Glean is going to run the indexers to collect all the facts that the indexers produce. Then we're going to have a derivation step where we run the stored predicates to run the queries and store it back in the DB. And then it's going to be online for service. Yeah. Okay. So target uses is another derivation example, a stored derivation example. And we're basically just going to flip the file xrefs that the indexer gave us and switch the order around. And this is effectively what we use to serve find references, right? Because it's just the other way around, and we don't need to do any further work than this. Whew. Okay. So deriving the code markup layer. In Angle, you use import of a different schema to pull in other schema files. Sorry, it's a bit small, I know. It's going to get bigger in a second. So we can have a code markup schema that pulls in example that we just wrote, CXX and hack, let's say. Because I said each of those have separate schemas, right? And the code markup file xref is going to have a file in line, but the destinations are stripped of all semantic information because we're gonna consolidate across all the different languages. So we're gonna do the derivation trick again, where the query is going to be some complex query that gives me the example file xrefs. The details of this part doesn't really matter. We're gonna do something similar for C++, right? C++ might have file xrefs, but we might also have PP xrefs because we're gonna have collected some information during the pre-processing phase. We also do some derivations of like declaration to definition relationships and back so that we can do those jumps, right? And so those might be in different predicates, but like the implementation details of that stuff doesn't really matter. We're gonna have the bar to say this code markup file xrefs is going to be some way of computing example file xrefs, or C++ file xrefs, or some hack file xrefs. And practically what we end up doing is pulling the logic out into a code markup.language schema. And so basically all of the code markup.language schema's predicates will be derived. And then the code markup schema is just going to OR across all of those. So you can imagine calling code markup file xrefs with a C++ file, or hack file, or example file, or any other language, and it'll just give you the file xrefs. It doesn't really care. Okay, back to C++ macro navigation. So we need to extend the source location because we kept it at just line numbers before, right? And as we discussed earlier in the macros locations, we need to keep track of the file locations, expansions, as well as spellings. So we can expand the lines into three different fields. We're going to call it spans, expansions, and spellings. And rather than lines, I changed it into a type called span. Just assume that's kind of like a std span. It's an offset plus length, whatever, right? So now this xref is going to store information about all the different locations. So for example, the record declaration S, the spans field will store the file location. The expansions will store the expansion location. Spellings location. So if your class doesn't get involved with macros at all, then the expansions and spellings locations will just be empty. You'll just have references from spans. And generally, you're going to have a one-to-one relationship between expansions and spellings, right? You're going to have like wherever there's an expansion, there's going to be some spelling associated to it. And so generally speaking, expansions and spellings will have the same length. So that's the source location. And the source locations are always going to be a single token, which actually has some different implications on the results. So let's see what I mean by that. So the target location isn't just some span, right? The target location, the target for an xref is actually more semantically meaningful because we're referring to a specific record declaration fact. And the record declaration fact has a location in it, but like, which location is that, right? We've talked about how we have file expansions or spelling location, so which one do we store? So first, let's change the line to a span. And so if in this case we have two examples where one record declaration is going to have a file location, and the define s expanded struct is actually going to have an expansion location, right? So we have two record declarations. Okay, well, this will collide, but that's a slideware error. But let's say that they have different names. But the point is that the location of the declaration are different. One is in a file location, the other one is an expansion location. But the question is like, well, shouldn't it also have a spelling location? And this gets pretty fun because the spelling location for a declaration, because we're talking about the full span, full range of the declaration, right? But what if we had this? Anyone seen horror like this before?
Yes.
Yes. Yes. So what the heck? Is this the spelling location? Because if I take the AST, get the begin of the range, and tell it to give me the spelling location of that, it's going to give me the struct. And then if I ask for the spelling location of the closing brace, it's going to correctly give me the spelling location of the closing brace. But like, I can't create a range out of those two results, right? Like, so generally speaking, what I've learned is that these file expansion and spelling locations are applicable for a single token, but not a range of tokens. And maybe we can do something here, like stitching different areas together. I don't know. And another thing that I should mention is that these schemas are generally, the design of the schemas are generally driven by use cases. And so if we don't really have a use case for it, we're not going to design a complex schema to represent that stuff. So, so the conclusion is that the record declaration range is going to be just either a file or an expansion location, and that's fine. But in terms of where we want to jump for code navigation, we still need some spelling location of some sort, right? Because like in the define S case where it's expanded somewhere, like you might want to jump to the S inside the macro definition because that's the actual location of where the definition code is. And so what we end up doing is introducing a separate name location of the declaration. And that's generally going to be a single token. Sometimes it's not, like operator plus is 2 tokens. We run into some issues there. It's fine for the most part. So the name we're gonna say, so here we go. The file location of the name is going to be what's highlighted there, and the spelling location is gonna be inside the macro. And so as a code analysis tool, you'll probably use the full location, whereas for code navigation, we're going to use the name location, because that's ultimately where we're going to jump to. Yeah.
So the name location is capturing the spelling location you've got in the
Correct. So the name location is either file or spelling, and the file and span above is going to be file or expansion. Yeah. I feel like I'm going too fast. All right. Any other questions so far? All good? Okay. So here's Glean. So this is being done by Glean now. It's the same code. So that worked before, but here we go. That one works now. This string thing that went to std string before goes to the string member. Aggregate goes to aggregate. That worked before too. This data didn't work before. We end up at a union. And this spelling to spelling jump, which looks like a local variable jump, also worked. And then this last stats jump also worked with CppNow as well. But so keeping track of all these different locations and indexing them and making use of them accurately is quite important to be able to deliver experience like this. And if we count so we have metrics for how many like navigations that developers do at Meta, right? And so we count like number of times that people had these activities. We keep track of like what the source token that was clicked on was, as well as the destination token that we took them to. So if those don't match, we'll generally say that's not like we failed to jump correctly. That's not correct, like completely true, because we have implicit conversions that will take us to a constructor and the site doesn't match the destination. But like by and large, it's a pretty good estimate. And the problem is, well, part of the problem I think is like not every jump is worth the same, right? When you have local variable jumps, like within a small function, yeah, people clicked on it and stuff, but like you could have done that yourself pretty easily. It's the external jumps into some mysterious file through some complicated dependency or code like this through a bunch of macro extensions that it's really hard to follow, where just being able to click on something is extremely valuable. So I just wanted to say that. And there's still a lot to do. So first, templates are indexed, but implicit template instantiations are currently not. And so what this means is, let's say we have some code like this. We have struct s with some function, a function bar with auto x. We call .x.foo. Now, when I index the templated bar, it it collects some information about it, but without the instantiation, it can't actually see the reference from x.foo to s::foo. S is foo, I mean, right? And so this needs to happen at the bar call site with s. And in fact, if that bar call with s doesn't exist, then there is no reference from x.foo to s::foo, right? And so my, I guess, short to medium term dream is to be able to find references, like imagine doing right click on s::foo, doing find references, and discovering x.foo, if and only if the bar was called with some s, right? And in order to be able to collect that kind of information, we need to index implicit template instantiations. Now, the trick is we need to design the schema that can capture that. And not only that, it needs to capture it in a data conservative way but is still representative, because otherwise our DB is just going to blow up and we won't even be able to serve it. And as the DB gets bigger and bigger, the query times get worse because it needs to look through more stuff and all that kind of stuff, right? So schema design for templates will be challenging, but it's something that I'm looking forward to do. Dealing with local edits is still very challenging, and this is because the Glean database is going to be a snapshot at some commit, right? So we're going to periodically index the whole world at some commit, but what if you have local edits? What if you're checked out on a different commit than the one that we have indexed, right? We are doing some work to serve the nearest commit to where you are locally checked out so that we have a better chance of it matching. A lot of times what happens right now is that for a lot of the areas of the code base wouldn't have changed, and so navigation works fine. And we also have some fun tricks with diffing the commit that we have indexed with your local commit, and then relocating the xrefs to at least be able to serve the ones that we do have indexed, right? And so if you add some code in the middle of a file, we might shift all of the xrefs that we have indexed below that down, so that when you click on it, we'll still, be able to do the navigation. Yeah.
So if I understand you right, that you generally index your main branch commits or something like that, and then when you say the nearest commit, you mean the nearest commit you've already indexed and you skip some sometimes, or you mean like you generally have the commit you generally have the main branch or the trunk branch commits already indexed?
Yeah. So
it's not a daily batch job and they just go to the previous day. It's like generally all the time. So let me just describe the situation today. So we do the index periodically, and we try to keep up with basically the trunk, right? The main branch. But we do keep the older DBs as well, right? And so if you happen to be close to that main branch, then we probably serve the latest DB. But let's say you haven't rebased in like 2 weeks, right? And people do that all the time. I don't get it, but people do it. So if they're doing that and we serve them the latest DB, then their experience might actually be bad, even though we're more up to date. And so what we could try is, they're basically like close to the commit that we indexed five times ago, or like 5 cycles ago. So, and we still have it. So we can still serve that. Right, so doesn't show up in your index. You probably have a whole other system to try to locate the nearest common commit.
Yeah. So that's a whole other thing. It's not quite indexed in the Glean, but basically, like when the server receives the request and it has the information about the local, the commit that they're on, we can try to.
It's a correlation ID and stuff.
Yeah, I mean Mercurial might have some API to help with that, something like that. I don't know. Yeah, David.
So say I have like a CMake codebase, which is really large,
mm-hmm.
and I want to adopt this tool. Like, how much effort is it going to be to build and get all this up and running? What does that look like?
Yeah, so the story isn't great there, to be honest. It's a relatively young project still. So we have integration for CMake, CMake as a build system, even though we use Buck internally. So you can check out the project and basically index a CMake project and get a database out. You can do Glean shell, like I showed you, and ask it a bunch of questions. That's kind of the current state. So from there, like serving, okay, so that's not true actually. There's also a Glean server that you can point to the DB, and then the server will respond to those queries, right? As far as like the rest of the tooling goes, the language servers that I used to show the demos currently isn't open source, and so that's something that I would like to change soon, hopefully. But so that's not something that's available to be just picked up right away. So that's part's a bit unfortunate, but yeah, that's kind of the current state. Okay, hold on. Zach had his hand up.
So I would imagine a major use case would be I want to make some kind of large scale change.
Yeah.
And I'm touching like maybe 1,000 files.
Right.
As I'm just monkeying with stuff. I have like some tooling maybe that does the 90% case and I have to fix up at whatever's left.
Yeah.
So I want to use this to explore the code around the places there's problems.
Right.
If I'm doing that against trunk,
Yeah.
I'm going to get pretty close.
Yeah.
But then I'm touching 1,000 files, and presumably this is the reason I'm doing this all at once is because it touches something low level and affects a bunch of things.
Okay.
So I'd imagine there would be 1,000 TUs plus that are affected.
Uh-huh.
Is there any way, like, do you have any support for or a roadmap for, doing sort of like a live indexing of things as you're going, and then having like an overlay of your database? So you've got the database with the stuff from trunk, and then you've got your view of the database, which includes some stuff you've indexed locally, and some stuff that refers to the big database. Anything like that so that you can do these kind of large refactors?
Oh, I see. Yeah, so yeah, I didn't touch on it at all, but we do have incremental indexing in Glean today. And so we can build a new DB off of an existing DB. And what that's going to do is figure out which files changed. And we're mostly going to rely on the commits to do that. And then we're only going to index the parts that changed as well as its dependencies and the reverse dependencies. But that's still going to be way smaller than the giant mono report that we have, right?
So this will work for like a long-lived branch where you're doing an experiment. It's going to work based on commits up to that branch, though, right?
Yeah. So okay. So this is fun actually. So we actually index every diff incrementally on top of an existing DB, and so in Fabricator, internal Fabricator, sorry, you can actually do code navigation there, and that's going to be off of the Glean index that's built off of that small commit, which is the diff, right? As far as like large refactoring and stuff goes, I think it can be used for that, but like you can for example like have a small commit, a large commit locally, get Glean to incrementally index that commit and then reevaluate, right? Yeah, and like ultimately like the goal would be to do that incremental indexing for like live code that's being edited, right? But like currently the incremental indexing is still a bit too heavyweight for that kind of operation. And so yeah, so like this is something I mentioned here is like, so like we still use CppNow, don't get me wrong. Great tool, and like even though I showed an example where Glean does better, CppNow still does better in a lot of the cases, right? This is just biased showing an example. But the integration with CppNow isn't great. And so I'm looking for better ways to integrate more seamlessly with CppNow because it's a little bit clunky today.
On that last point, how can you re-index on deduplicated data like that? Like if you lose a reference, like in that translation unit upgrade, how would you know that something entirely disappeared versus it just disappeared on the first time you saw that reference or something like that? Am I making sense?
Sorry, do you mean,
so you say you're deduplicating records as you're indexing. You said something like that earlier.
Yeah.
Right. So like if you re-index a translation unit that changed,
if you re-index a
how do you
translation,
know you didn't just lose the first time you get that record versus the other n minus
Oh,
one times you didn't pay attention because it wasn't the first time.
Oh, it's because the DB isn't just live and receiving facts and evolving. It's completed.
Okay, so okay.
And so the way we do it
isn't lost. It's just abstracted away.
Correct. So when we do incremental indexing, the old data is just hidden.
Okay.
And so what's cool is like before. So like okay, we talked about like having 5 different DBs at 5 different commits, and then like serving different people and different point in that commit, right? If you have 5 different incremental indexes on top of a full DB, you actually can get all 5 of those views.
Okay.
So you can query the stacked DB effect. So this is what we call it, right? So there's a completed DB. There are 5 stacks on top, and you can look at the DB through any of the stacks, and it'll give you the view at that point in time. Yeah. As far as like things that are getting lost and stuff, that's handled via a model where we have ownership. And so in the DB, the facts have ownership of other facts. And so typically a file fact will have ownership of all of the facts that are related to it. And so it knows that if this fact is changed and we need to reindex or whatever, it knows that like all of the facts that it owns also need to be updated and stuff like that. Yeah.
So it sounds like the only user tool you have right now is this like command line query thing. I'm wondering what would it take to get like a web-based code navigator, which uses this as a backend?
Yeah. So the answer is we actually already have it. Internally, we have a web-based code navigation tool, a code browser, I mean. And it actually already uses Glean to power that stuff. The problem is, I don't think there's a roadmap to open source the code browser. And so I think if there is a code browser out there that is pluggable with some data, then it could use Glean as the backend for that. But the code browser that we have internally that already uses Glean as the backend, like I don't think there's plans to open source that, unfortunately. Yeah, Dave.
Yeah. So I guess like for monorepo, I can just imagine like it just getting a single snapshot and everything. But like, how would it work for like if there's like multiple repo and then like you were starting from different path and then like
right.
Yeah, like was there any experiments with that, or like is that enabled somewhere, or?
Yeah, so we have an example of that today. Okay. As far as like separate C++ repos and jumping across them, we don't really have one because we don't need it for work. But we do have an example where we have 2 different DBs that we want to talk to each other, which is C++ to Thrift. So we have a giant C++ DB, which has all the C++ information. There's also this Thrift IDL, which is kind of like protobuf. I don't know how many people would have used it, but it's basically an RPC protocol, right? And so we have a Thrift compiler, which produces Glean facts. And so we have a Thrift DB, which has information about the Thrift IDL. The Thrift compiler also generates C++ code, right? And so when we go and index C++, the xref that we find are C++ function invocations to generate, like Thrift generated C++ invocations. Thrift generated C++ functions. And so typically what ends up happening is when people try to do the jump, they end up in generated code, which isn't very useful. Half the time, actually, what really happens is the file, like, you don't have that file generated, and so it doesn't go anywhere, right? Which is even worse. And so the cross repo thing that we've done is to link the generated code, the generated C++ code, to the Thrift IDL and do the jump across so that you can go from C++ to Thrift directly. That works today. Now, the problem is that you're right. So like they could be indexed at different commits, right? And so currently what happens is we just match symbol IDs. And it doesn't quite respect the same commit thing. So it just kind of keeps jumping to the latest as you navigate.
Yeah, I would imagine in that use case, you would probably also need file identities that were keyed on the repository they came from, so that you could, like you couldn't just say file, because you might have the same file in multiple repos. You'd have to say, well, the file from this project.
Right. Yeah,
we also
yeah.
need to know from a header file, even though you came from the translation of your project and reached the header file, it is actually a header file from that other project. So you need to have some notion of like project ownership of a file as installed in multi-test or something like that.
Yeah.
It'd be interesting, but I think you can do it.
Yeah, I think like this is partially like part of what I'm so excited about of the project in general is that the schema can be arbitrarily complex, right? Like as use cases come up, you can design it in such a way that you can serve that information. The facts generation isn't tied to any technology in terms of like it needs to be a language front end or whatever. It could literally come from the linker, right? And so actually, I think okay. So let me just cover the rest of this slide, and then we can keep talking. So lib incremental is something that I saw go into Clang, which apparently is associated to Clang REPL, which is, I think, a C++ interpreter. And so it's supposed to do incremental parsing. And I don't really know what the API is supposed to look like, but the term incremental parsing sounds like useful enough for a use case like this, where we want to do like index C++ information live as edits are happening. But these are like things that we need to explore to improve the experience. So there are other things like support for various platforms and environments. I am currently in Windows hell trying to migrate the indexer to build on Windows. It's been a miserable experience, but I'm doing it. So the idea is to index files that can only build on Windows. So if you have files that include windows.h, but we only have indexers that run on Linux, then, well, you open that file, it's not going to go anywhere, right? And so, but if we ran the indexers on Windows, then we would get that information that you can actually use to navigate on a Linux machine, right? Because it's just going to be a call to a server that gives you information, and you can just follow their directions, right? You don't need to build anything locally. It gets interesting as well because now we're going to have like pound include variant, and we're going to have like the Linux based like libc++ or libc++, traces of that, as well as like MSVC implementation, and like which one do you actually jump to? Does that depend on like what machine you're on? Like, what if you're on a web-based code browser? Which one do you want, right? Like, there's some UI questions around how to actually serve this information. But again, like there's value in being able to separate like how we're gonna use that information versus like not having the information at all. And so the first step is to like collect the information, and then we'll figure out how to expose it in a nice way. But we need to collect the information first. And yeah, and we can build more tools on top of it, right? We can potentially build like build time insights because, as I said, the generation of facts isn't limited to any tool, any specific tool. And so your build system could write facts and say like, hey, the most expensive translation unit in your project was this, or like this library. This library is included in so many different translation units, but like 90% of them only use 10% of it. 90% of the files only use 10% of that library, so maybe break it up into like that library light, which 90% of your users use, versus like the rest of the heavy machinery that the 10% of the users need, or something like that. So this is all things that you can imagine building once you collect all the information, right? People ask me about modules all the time, and I don't really know anything about them. But like the build time issues at Meta are like bad enough that we need to do something about it. And if we're gonna somehow get to modules, like, okay, I said I didn't know anything about it, but I did look into it a little bit. And like, as far as like hand crafting your code base to get modules, it seems pretty infeasible. And I think a tool like this could help with that kind of stuff where you can, because you have full visibility of the whole project, right? Like even in a single header, you have information about like how exactly it's used in weird ways in which like previous includes affect the subsequent includes. Like we can have all that information. And so maybe there's something we can do to help migration to modules. I don't know. I floated earlier that like we could write facts from the linker. You know, if we do that, maybe we can detect some ODR violations. I don't know. These are just like ideas that I had of like other tools that we could build once we have rich information about your source code. So that's kind of all I had here. I have some bonus stuff that I could show, specifically for like language server stuff. But let me take some questions first. Yeah, David.
So Google's Kive project
Yeah.
is obviously very similar to this one, and that had been open source for several years, very
Yeah.
interesting.
Right.
But because of the lack of a code browsing tool,
Yeah.
it had like such a minuscule impact on developers' lives.
You're
And
right.
I would hate for this project to come to that same end. I mean, it's just great internal for Facebook because you can
Yep.
use the code browsing tool.
Yep.
Like, what is it going to take for us to actually bridge that gap and have that impact? If maybe your tool isn't something you want to open source, but like, is there openness to collaboration so that such a tool can be made? Because I think there's so much potential, and it'd be so sad to not see like this get in users' hands.
Yeah, exactly. Yeah, thank you for saying that. So part of the reason I'm here presenting it is to, first gauge like what the interest level is. Like, as I said, the Glean started in 2018-ish. It got open sourced in 2021. So, and I've been working on it for about 2 years. But there's still so much work to be done internally that there hasn't been all that much work done externally to help like the community, right? But like personally, like I care about helping the community as well because I love events like this and helping other developers. And so I think, okay, so as far as like my plan goes is to open source the LSP. So let me actually describe that now and then. So the LSP is something that Microsoft came up with, and you might have seen this picture before. But basically, it's to solve integration problems with different editors, right? And so with no LSP, you have this mess of a situation where like all these different languages need to like support all these different editors each individually. We can have this LSP layer that we can agree on as to what the format is, and the language servers can just speak LSP as far as the requests go, and the editors can agree on how to send that request in the form of LSP, and then we can just support all these different editors for different languages, right? So where does Glean come in? This picture is kind of similar, right? Because we have this IDEs situation, which is on the right-hand side, and we don't really care about the AST stuff because that's like individual details, but we can shove a Glean language server in the middle, and now the Glean language server doesn't actually have to talk to any individual language servers directly. It can just talk to Glean. In fact, in part because Glean already talked to those individual languages itself already, right? And so this Glean language server is the thing that was used in my VS Code demo that I showed. And that's the thing that's not currently open source, but I don't think it should be that difficult to open source it. Currently, it's written in TypeScript, but it could be written in any language, right? So right now, it's a bit difficult because there's a lot of like internal stuff that's kind of tied into that project. But to be honest, like if you look at this diagram, like, so Glean language servers needs to speak LSP to talk to the editors, and it needs to be able to send requests to Glean and make uses of it. Like the logic is not that complicated, and so I think this is the smallest, like high impact thing that we could deliver for the community. As far as like the code browser stuff, I don't know. Like I don't know if there's maybe a code browser that has some like an LSP kind of protocol that we could speak, because then we could just plug into some other code browser and just provide the information that way, right?
I
Yeah.
actually think the header removal use case you brought up is one of the more interesting ones because any particular, like for example, claim-based query for that kind of information is going to be incomplete by the nature of the compilation database you're operating against being specific to the CppNow mode that you're in.
Yeah.
You wouldn't necessarily see, in the 32-bit mode, you also have these other headers. So they're not really unused. It just looks like it's you and that kind of thing.
Right.
But
We
I think that's interesting because it's really not, like as you pointed out, it's really not a solved problem right now, really.
Right.
Might be difficult to make it something you do on every CI pass, but it might be something you can do as a more asynchronous, once a week I'll give you a bunch of tickets for these, the ones you should probably clean up and that kind of thing, right?
Yeah, I agree.
It might be easier that language to work all for certain kinds of things. So.
Yeah, maybe so. I think, we still have the same, like those problems of like, it looks unused to us, but like someone's building it by passing in the flag explicitly.
Okay, we can narrow it down to, stopping transitive with your includes and start being direct and that kind of stuff.
Yeah.
But you still need the annotations because,
Right.
I meant it the other way, but then you can make that into a model, right? So,
Yeah.
I have,
But yeah.
I have another question,
Yep.
which is, have you been seeing the work on reflection and do you think that would be problematic to model at all, or is that something you think would be natural?
Yeah, so,
It smells like a macro, I just wanted to know if you had a quick take on that.
yeah, not really. I think Anastasia has mentioned some issues that JetBrains has looked into that reflections could cause for their tooling. Is that accurate? I haven't really looked into it much and analyzed it for myself, but I don't know. In some way, I don't think it matters that much to us, at least for this project today, because like I think a lot of the concerns has to do with like speed, right? Being able to do things fast, and like we're not quite there yet, and so like in some sense like I haven't gotten to solving that problem.
It looks a little bit like a macro because there's kind of a expansion kind of thing happening.
Yeah,
So you might even be able to use your naming model, but I haven't thought of it. You'd be able to think about that even I think.
Yeah.
Because you want to say the same kind of things like show me, click on the thing to go to the site of the reflection, and you go to the site of the use, like that kind of stuff.
Right. Yeah, I'll give that a thought. Yeah, but I'm not sure today. Yeah.
So this, if you can't answer this question, that's totally fine. But I was just kind of curious, so I don't know, but I assume Meta has a pretty non-trivial C++ code base. Like, what do indexing times look like for this, out of curiosity?
Yeah, I don't know if I can answer that.
Okay.
Can you compare it to like a per translation unit to a passive clang? Is it the same order of magnitude as like a clang parse?
That one I'm more like I'm not sure. I know the answer to that.
Okay.
But I'll say that it's I say less than half a day.
Okay.
Yeah.
Just a quick question.
Yeah.
Does Glean support C?
Yes.
Yeah.
This is
Say it again.
it can support C/C++ even. Which can index the C parse and then the C++ parse.
Yeah.
Of the same method file.
Yeah. So another thing that I'll mention actually, just because we have time. So SourceGraph is another company that does code indexing, and their tooling is actually quite good. They have a protocol called Skip. It's SCIP, and that is like closer to like a least common denominator kind of model, but it's useful to be able to serve all these language agnostic tools, right? And they already have indexers for all these different languages. JavaScript, I think TypeScript, I think Rust produces skip as well. Also, like all these different indexers already produce skip indices. And so the flexibility of the Glean schema, we've actually leveraged to write a skip.angle. So we can actually ingest a skip indexer that produces skip-based information, ingest that into Glean, and then use that as the basis to serve those languages. And so, so yeah, I think Java, Kotlin, Scala, TypeScript, Rust are all supported by Glean by leveraging the skip work that has already been done. And so, you know, like spinning up a new language support has actually been less work than, you know, designing a new schema for every language that we want to support. So that's been actually quite nice. But yeah, going back to what you said, David, I think you know, it's an open source project. I think that's a good start, right? Like if I was coming here and it wasn't an open source project, like that would be a rough, you know, starting point for us to like do anything for the community. But the fact that Glean itself is open source, I think, is a great start. You know, and I think we need some like at least just one useful tool that can be powered by Glean, and that would be a really good start, right? But I'm looking forward to it. I'm excited about the project, and hopefully we can do something cool. Okay, let's wrap up here.